Hello again. In our previous video, we examined some of the unique properties of water. In this video, we're going to try to explain some of those properties based on the molecular structure of water and some of the intermolecular forces in between water molecules. So this will probably be two videos, and in the first video, we're going to focus on bond dipoles and molecule dipoles, and then in the second video we're going to focus in on hydrogen bonding. So now to understand bond dipoles, we need to understand this concept of electronegativity. And electronegativity simply is the measure of an attraction of an atom for electrons in a chemical bond. So how badly does a particular atom want those electrons? Okay, and the greater the electronegativity, the more an atom attracts those electrons towards itself. And in terms of explaining the trend of electronegativity, we can use this picture here. So the least electronegative atoms are going to tend to be towards the lower left-hand corner of the periodic table, whereas the most electronegative atoms are in the top right corner. So fluorine is our most electronegative atom in the periodic table. Now, that allows us to move on to this concept of polarity and polar covalent bonds. So this, in a bond, a covalent bond, we have two atoms involved, and a difference in electronegativity between those two atoms causes the bond to be polar. So an example here would be a bond between hydrogen and oxygen. Now, oxygen is more electronegative than hydrogen because it has a value of 3.5 versus 2.1. And as a consequence, more of that electron density goes on over to the oxygen, giving it a partial negative charge and the hydrogen a partial positive charge. And this gives us what's called a dipole moment, and we denote that with this arrow that points towards the more electronegative atom. And if we have a covalent bond where we have two atoms in the bond that are identical, if they're identical, they're going to have the same electronegativity, and it's going to be nonpolar. Okay, so we can quantify or measure the strength of this dipole moment using what's called, using the dipole moment. This is the strength of the dipole. There we go. And that is equal to the difference in the charge between the two atoms and the distance between the two atoms. And so here's some examples of commonly encountered polar bonds and the strength of their dipole moment. So you can see some bonds are polar but not very much so, like a carbon-hydrogen bond, whereas a carbon-nitrogen triple bond is really strong. Okay, it has a very strong dipole moment. All right, now we can go from talking about polarity of bonds to talking about polarity of molecules, and they're not necessarily the same thing. So it happens that a molecule can contain polar covalent bonds, yet as a whole, the molecule itself is nonpolar. And so we have to account for the shape of the molecule. Okay, so let's look at these two molecules. Now, these molecules both have polar bonds in them. Okay, however, as a whole, the water molecule is polar, but as a whole, beryllium dichloride is nonpolar. Okay, and the reason we have that difference in the molecular polarity has to do with the shape. Water is bent, whereas beryllium dichloride is linear. Okay, in beryllium dichloride, these dipole moments, though we have them, they are going in completely opposite directions with the same magnitude, and so they cancel each other out. And I think the textbook uses this nice illustration of a tug of war. Imagine you had two teams pulling in completely opposite directions, but they were like very equally matched. You can imagine that tug of war would last a very long time. And if you imagine that they were completely evenly matched, then theoretically nobody would ever win. It would be like the tug of war that lasted forever. Okay, that would get boring after a while. Whereas here, what we've got is these bonds kind of cancel each other out in one direction, but they're kind of going the same way in the other direction, and so that makes this molecule polar. Let me give you another example here. So here I've got a carbon-chlorine bond, okay, and it's a polar bond because chlorine is more electronegative than carbon. Now let's look at it in a couple molecules here. In this molecule, if we kind of look at the dipoles, they kind of cancel each other out maybe in some directions, but not in this direction. Okay, so we end up with a net polar molecule. In this molecule, they're all canceling each other out. Okay, and it might be a little hard to see that, and that has to do with the fact that we're trying to depict a three-dimensional molecule on a two-dimensional surface. And so these bonds that just look like straight lines, they're supposed to be in the plane of the slide, whereas this bond, which we call a wedge, is coming towards us. This bond, which is a dash, is going away from us. And kind of overall, we would say these vectors kind of cancel each other out in all directions. And so that makes this a nonpolar molecule. And again, the key idea here is that we need both bond polarity and molecular shape to help determine whether a molecule is polar or not. Bond polarity is determined by relative electronegativity of atoms involved, and molecular shape is going to affect the sum of the vectors of the bond dipoles. Okay, so let's try a little exercise here. So here I've drawn some molecules where I've replaced the actual identity of the atoms with colors that are meant to represent their relative electronegativity. So blue is the most electronegative atom, cranberry is kind of middle in electronegativity, and white is the least electronegative. And so what I want you to do is I want you to look at these 9 molecules, and which all have polar bonds in them, and I want you to see if you can predict which ones have a molecular polarity of being nonpolar, and which molecules are overall polar in their polarity. So go ahead and pause the video, see if you can figure out which ones are non-polar, and in the couple seconds I'm gonna continue on to the next slide with the answers. All right, it's time to reveal the answers. Okay, so you'll see here I've got the bond dipoles here. I'm sorry, the molecule dipoles. And if the numbers are non-zero, these would all be polar molecules. But if the numbers are 0, these are non-polar molecules. So you can see we have 4 of these 9 molecules are non-polar. And they all contain polar bonds. However, because of the direction these bond dipoles are going, they cancel each other out in different ways. So here it's like we've got a tug of war where there's 2 teams involved. Here there's 3 equally matched teams involved. Here there's 4, okay? And so on and so forth. This one is probably one of the harder ones to see because you're imagining a tug of war where you've got 4 teams pulling in 4 different directions in space. And so it's not like you're sitting on this planar field. It's like all throughout space. So it's a little more confusing. Okay, great. And that's going to conclude this video. I'm going to do hydrogen bonding in the next video, just to keep these videos from getting too long. So thanks for watching.